All right, welcome to the second part of section 4.3. And we're going to start things right off with a little thing called the Pythagorean identities. So, the Pythagorean identity in trigonometry come from where you'd expect. If we have our triangle, so a right triangle. And if we have a right triangle, we know that the relationship between the sides is a squared plus b squared equals c squared. All right, so that's Pythagorean theorem. Well, let's take a look at this another way. Let's think about the sine of angle A. The sine of angle A would be A over C. And the cosine of angle A would be B over C. And if I rearranged this equation, then I could turn that into the statement of A equals C times the sine of angle A. And I could multiply by C on both sides on this one, and I could get that B is equal to C times the cosine of A. And if I now use a little substitution, I can substitute these two statements into the Pythagorean theorem. So I know that A is C times sine of A. So A squared becomes C squared sine squared A plus B, we can substitute in, and I get C squared cosine squared A equals C squared. And if I then divide everything by C squared, we get the statement sine squared A plus cosine squared A equals 1. This right here is known as the Pythagorean identity. And we can take it a couple steps further. There's like 3 different Pythagorean theorem or identities that work in trigonometry. And they all come from this statement right here. So this is the main one that you need to learn and memorize. Sine squared plus cosine squared equals 1. The next way we're going to know the Pythagorean theorem is we are going to take what we just derived, sine squared A plus cosine squared A equals 1, and I'm going to divide all 3 terms by cosine squared. And by doing that, I now have sine over cosine, the quantity squared, sine squared over cosine. So sine over cosine is tangent. So this becomes tangent squared A. Cosine over cosine is 1. So this is just 1 squared, or 1. And 1 over cosine is secant squared. So here is a second way that you will find handy to know that tangent squared plus 1 is secant squared. Okay, and if you don't know it, but you desperately need it, you can recreate it by doing the very simple math that we just did. And then there's a third Pythagorean identity, and that's going to be formed by now dividing by sine squared instead. And let's see what that creates. So this time I'm going to divide by sine squared. Sine squared over sine squared is 1, plus cosine over sine, that is cotangent. So this is cotangent squared of A. And 1 over sine is cosecant, right? Yeah. So we have cosecant squared of A. And this is the third way to know the Pythagorean theorem. The one, the one I have memorized the best, of course, is the first one. I know there's a relationship between tangent squared and secant squared, but often I can't remember which side the one is on. And the same thing with cotangent. I know cotangent squared is related to cosecant squared, but unless I'm in the middle of doing a bunch of problems, then I let that kind of drift out of my memory. So this wouldn't be surprising. You might have to look these up, but ideally we get these memorized. The one that you definitely need to have memorized is the sine squared plus cosine squared equals 1. And then again, like I said, if you desperately need to know what these are, if like there was a test and I said name all three, well, you can easily derive the other two knowing the first one. Okay, so the theme of 4.3 is kind of just getting used to these basic trig identities. If we kind of go back and scroll up to the top and take a look, that's pretty much what we started with, right? We reminded ourselves what sine, cosine, and tangent mean. And then we talked about how we can rewrite and think about cosecant, both as we could think of it as the hypotenuse over opposite, but really we can also think of it as 1 over sine. All right, so we've got our reciprocal identities, and then you've got your quotient identities, which was how we can write tangent and cotangent in terms of a quotient of sine and cosine. So tangent is sine over cosine, cotangent is cosine over sine. So we talked about that. And then we talked about these, which are known as, by the way, I don't think I ever named them. These are known as the co-function identities. Co as in complement. So co-function identities. T-I-E-S. Not even close. Identities, whatever. I can't spell. Co, again, for complement. Complement. I'm doing this, by the way, in the early release at the end of the day, and I am sort of cooked as I pick up your language. And then we have then our Pythagorean identities. All right. So now what are we going to do with these things? We are going to begin with some very basic ones. When we get into the next chapter, we'll do some more advanced ones. But for now, what I would like you to do is identify or use trig identities to confirm that the left side of the equation is equal to the right side. In other words, that these are identities. The definition of an identity is it doesn't matter what the variable is, the thing will always be true. So like the difference between an identity and like just a standard equation, x equals x is an identity, right? Doesn't matter what x is, the statement is always true. It's an identity. Versus like x plus 1 equals 5. That's not an identity. That depends on getting it right, depends on having the right x value. So not an identity. So these are identities. Cosecant of theta, secant of theta should equal 1 no matter what. And our job is to figure out how we can show that that is the case. And the way we're going to do it is we're all going to do it the same way, is we are going to look at this as like not even so much of an equation. We're going to just focus on the left side of the equation. So we're going to focus on this and think of this as our target. And don't think of it as an equation so much, because what we're not going to do is we're not going to move things from the left side to the right side. We're not going to use our equation operations. We're just going to do math on the left side and see if we can turn the left side into the right side by itself. All right, this will make more sense as we do a few. So the cosine of theta times secant of theta is equal to 1, supposedly. So this one's pretty straightforward. When we're doing these identities, what we're going to do is we're going to just basically do one step at a time, and we're going to be very methodical. It's kind of like doing a proof in geometry. We're going to be very specific. So I'm going to do one thing, and I'm going to only change one at a time, and I'm going to show all my steps, even if they seem obvious. Secant of theta is also known as 1 over cosine of theta. And then, again, we're not going to jump ahead. We're going to be very methodical. When I multiply these together, I get cosine of theta over cosine of theta. And cosine of theta divided by cosine of theta is 1. So we get 1 equals 1. So I have proved that the left side equals the right side, regardless of what theta is. It does not matter. At the end of a proof like this, we're going to put a little box, and this box tells the reader of our proof that we are done. And if you ever are making a move that doesn't seem perfectly obvious, or like if you were think about like as a teacher, if you're going to teach this, if you think your kids will be like, wait, how did you do that? Then what we're going to do is off to the side, we're going to leave ourselves a little note. All right, so let's look at part B. So what can we do on this one? Well, we could do all kinds of stuff. But again, remember, we're only doing math on the left side. So our basic rules are we can convert things into versions of themselves, like we did over here. Secant and 1 over cosine are equivalent. We can do whatever math is being said to do over there. And then there's a couple other items that we'll get to. So a couple of ways we could approach this one. One would be a difficult way. I think it would make the problem harder. Is I could turn secant into 1 over cosine. I could turn tangent into sine over cosine. And then I could worry about adding those fractions together. And I could do the same thing over here. But eventually, this problem is requiring us to multiply, right? Take this thing, the left side times the left part times the right part. So let's just do that from the beginning. So I am going to multiply. So secant theta times secant theta is secant squared theta. And secant times that is secant theta tangent theta. And tangent theta times secant theta is another, but this time it's positive, secant theta tangent theta. And then tangent times negative, we have negative tangent squared theta. And I should have said from the beginning, what's the reason why do I want to do this other than like turn secant into like sines and cosines? That's because I recognize that these are conjugates of each other. And I knew that when I multiplied them together, we would get a lot of things canceling out. And sure enough, we have those two terms cancel out. So now we're left with secant squared theta minus tangent squared theta. All right. Now, again, we're trying to equal 1 here. And so what can we do to make this equal 1? There's a couple of approaches we could take. What I'm going to choose to do is I'm going to go back up and look at our Pythagorean identities. And I wanted to find this one. Here's a statement that says secant squared equals tangent squared plus 1. So I'm going to come down here, and I'm going to replace secant squared with what it equals. Just like I did over here. I replace secant with what it equals, 1 over cosine. So I'm going to replace secant squared with 1 plus tangent squared theta. Then I still have minus tangent squared theta. And then, of course, tangent squared minus tangent squared is 0. So then I have 1 equals 1. Okay. So if it isn't obvious what happened, you could leave a little note. So off to the side, you could say, note, secant squared theta equals 1 plus tangent squared theta. In other words, reminding people, hey, don't forget, we have a little identity that lets us do that. And I just jumped. Come on back. Okay. All right, let's see what else we have. Do we have a couple more examples? I do not. Okay, so hopefully you get the idea. There's some very basic questions like this in the homework, so go ahead and practice those. Again, keeping in mind, despite your desire to ignore the rules, these are all going to be done the same way, only math on the left side. Okay, so when in doubt, do whatever math you have or make some easy conversions using our identities and see where that takes you. All right, and then I've got several story problems here. I don't know that we need to do them all. I just wanted to have them ready in case we did. So one way that we're going to use trigonometry is, and one way trigonometry is legit used out in the real world, is finding unknown distances and angles in situations where maybe I can't just measure them. Look at this scenario right here. Let's go ahead and do a little zoom out. All right, so we have a surveyor standing. Here's the surveyor. standing about 50 feet, something they can easily measure from the base of a very large tree. The surveyor uses his equipment and measures an angle of elevation to the top of the tree as 71.5 degrees. How tall is the tree? Okay, so we're going to, with absence of anything telling us otherwise, we're going to assume that this angle of elevation is being measured from the ground level. Okay, not maybe at eye level. We're going to assume that this tool is on the ground, and so it doesn't have an initial height because that would impact the overall answer. Okay, so if otherwise it doesn't tell you, we'll assume it's on the ground. So it doesn't take us much to see that all we've created here is a right triangle, where the tree in question, they've labeled as Y, that's the height of the tree. We know we're at 50 feet out, and we're going with the assumption that the tree is straight up and down. The angle of elevation, whenever you're talking angle of elevation, what it's talking about is from horizon, from looking straight across, and an angle of elevation is what do your eyes do, or what does the tool do to look up? Okay, so this is known as the angle of elevation. If you have an angle of depression, that's the same thing. This is maybe I'm standing on a cliff, right? So I'm standing up on a cliff and I'm looking straight out, and then I look down. So the angle of depression would be this angle right here. So that would be an angle of depression. And honestly, the trick on getting most of these questions right is making sure the picture you draw represents what they've said. All right. So in our case, the angle of elevation is going to be this angle right here, and this angle is 71.5 degrees. So what do I want to know? I want to know the height of the tree. So now we just use a trig function that'll relate the things that we know to the things we don't know. So I could use sine, I could use cosine possibly, but I don't have any information about the hypotenuse, and so that really wouldn't be very helpful. What I have is from the opposite angle, from the angle, I have the opposite side and the adjacent side. That sounds like tangent to me. So I'm going to write what I know. I know that the tangent of 71.5 degrees should equal whatever the height of the tree is over that 50-foot length. And so I can then multiply to solve for y, multiply by 50 on both sides. And I get y is going to equal 50 times whatever the tangent of 71.5 degrees is. I don't know the tangent. That's not one of the ones I have memorized. It's not one of our special triangles. So it's time to use our calculator to get an approximate answer. So make sure we say approximately equal to. All right, I got to check my mode because I'm supposed to be in degrees. My calculator is in degrees. So now I just need to tangent of 71.5, get that answer, and then multiply by 50. So it looks like y equals approximately 149. And let's go to, I don't know, pretty standard 3 decimal places unless it says otherwise. 0.434 feet tall. Okay. Let's try another one. All right. You are 200 yards from a river. Rather than walking directly to the river, you walk 400 yards along a straight path to the river's edge. Find the acute angle theta between this path and the river's edge. So I think what they're saying is we're starting right here, and instead of tromping through the bushes and going this way, we're going to take the nice easy path to get to the river. And the question is asking, what would this angle be? Now, why do I care about this angle? I don't know. Maybe you're the surveyor. Maybe you've got to build the sidewalk. And so I need to figure out at what angle I need to go, knowing I'm supposed to end up here and be 400 feet long. And you need to know at what angle to start laying the path, right? Either way, what we need to do is we need to find a way to relate the angle to the known information. And it looks like I know information about the opposite side and the hypotenuse. So it seems to me that sine of theta would be what I want to write. So the sine of whatever theta is should equal 200 over 400. And the sine of theta equals 1/2. All right, at this stage in the game, we haven't really got into what math we specifically need to do to find theta. But at this stage, what we're going to do is we're going to pause for a minute and say, is this something I know? Do I know an angle that has a sine of 1/2? And the answer is yes, I do. And if I think about it long enough, I find on my unit circle that this angle right here, this is 1/2 and this is √3/2. That is our pi over 6 angle. So I know that theta equals pi over 6, or theta equals 30 degrees. And I just know that because I recognize this as one that I'm supposed to know. All right, I think I got one more. Pretty basic. Find the length of C on top of this skateboard ramp that this cool guy is skateboarding on. So I have my right triangle. It looks like I have a sine relationship. So I'm going to say the sine of 18.4 degrees equals 4 over C. Now, I could, since it's 4 over C, now my variable's in the denominator, I could start thinking about, oh, maybe I should be doing cosecant, but I can't do that on my calculator. So we're not going to mess with it. We're going to leave it just like it is. So don't be the kid that says, ooh, I need to divide by 4 to get C by itself. You can do it, but you don't get C by itself. You have 1 over C, right? So let's make sure we're very clear about this. You make this 4 go away, it's not suddenly C equals. It's 1 over C equals. So what I would choose to do is I would just go, and I would do this all mentally. I would go through the mental progression of multiplying both sides by C, giving myself C sine of 18.4 degrees equals 4. And then knowing I need to get C by itself, I would now divide by the sine of 18.4 degrees. So C equals 4 divided by clear sine of 18.4. So that's approximately, anytime we use a decimal approximation, make sure you use approximately, 0.31. And it's a good time to talk about this. We talk about using 3 decimal places, but we don't necessarily want to use 3 decimal places in our work. We're talking about rounding at the end. If I round to 0.315, then I'm introducing error right now. That now when I do math with, I'm going to compound that error depending on the math that I do. So whether you write it down to 3 decimal places or not, what makes a lot of sense is for us to keep it in our calculator as the bigger number and do the math with the bigger number. Now, I have put myself in a bit of a jam because I have divided, like I'm super lazy. I want to keep this number, but now I need to do 4 divided by that number. And so what I'm going to do is I'm going to just make really good use of the inverse button. So what that means is I'm going to intentionally divide wrong. So I'm going to divide by 4 because that would be wrong, right? So I'm going to divide by 4 and I get that answer. But that is the reciprocal of the right answer. So now all I need to do is flip it over. And so 4 divided by 0.315 is approximately equal to 12.67. And now I'll round to 2 decimal places. And this is feet. All right, I hope this makes sense. These are some pretty straightforward story problems as far as story problems go. The key is make sure you draw an accurate picture, and then you're going to be in good shape. All right, I hope this made a lot of sense, and we will see you in class.